So the idea here is basically this will be my life flashing before your eyes, so to speak. The first Earth satellite, Sputnik, launched when I was in middle school, and just 11 years later, when I graduated from graduate school, my first job was working in the Apollo Lunar Exploration Program, shown on the left there. Essentially a postdoc working in essentially training the astronauts to go to the moon in geology, landing site selection, where do we go, traverse planning, what do we do, and then of course being in mission operations for Apollo 11 through 17 to actually assist the astronauts when they were on the moon and debriefings when they came back. This is absolutely amazing beginning and was a real cornerstone in our understanding of the terrestrial planets. Since that time, in about 1973, in the middle image there, I've been engaged in essentially exploration of the solar system with a variety of national and international missions all the way out to the outer solar system with Galileo and other missions. During that time, I got really excited about exoplanets, knowing both Brad Smith and Rich Terrell when the Beta Pictoris days and beyond. I've always been excited about exoplanets. And next slide, please. I was really honored, actually, to be asked to give a plenary talk at the 234th AAS meeting in St. Louis in June, where I presented a synthesis of what we had learned and where we were going from a not just solar system exploration point of view, but an exoplanet point of view. Next, please. So what has happened in the first 60 years of plus years of space exploration? From my perspective, there were two parallel revolutions in understanding in 60 years. The first one was global plate tectonics, which of course we all take for granted these days, but indeed this completely changed our perception of the Earth as a planet. It was an integrated system that worked, in fact, in an integrated way. This is a big, big revolution in understanding and perception. And the second, perhaps best exemplified by the Apollo 8 view of Earthrise, is indeed the context of the Earth in the context of the solar system. This changed our complete vision of what was going on in terms of terrestrial science, and in fact ushered in the era of comparative planetology. Next, please. Now, of course, we've had 60 plus years of space missions. I mean, this is just an incredible attempt to get all those missions onto one slide. And in that 60 plus years, we not only have gone with 6 human exploration missions of the moon, but planets have really changed from astronomical objects to geological objects. Now, that's not an insult. That's not saying you're out of business. Astronomers were busy, of course, charting new frontiers, finding huge numbers of Kuiper Belt objects, and really understanding what was going on with exoplanets, etc. So this is really the beginning and a good example of how our activities complement one another. Next, please. So what were the some of the insights that we got? Well, indeed, the moon initially was a major insight in the missing chapters of Earth history. If you consider, as we show in the lower 2 slides here, the history of the planets, the history of the Earth and the moon as a clock from the origin of the moon all the way around to today, and look at the percentage of the surface that exists from that time, you can see for the Earth that essentially 60% of the surface of the Earth formed in the past 200 million years. That means that the first half of the solar system is woefully underrepresented and, in fact, largely gone. On the other hand, when we look at the moon, there it is, the complementary picture of the earliest parts of solar system history. This is an amazing new perspective. It revealed what was probably going on in early Earth history. Next, please. And indeed, we were able to work our way through the solar system in the last 60 plus years with all those missions, in particular for the terrestrial planets, taking a look at the differences in the planets in terms of their position in the solar system, in terms of their size, in terms of the density of the planetary bodies, and indeed, presence or absence of an atmosphere and what that meant. Next, please. Now, one of the things we found out, of course, was that we were able to get this complementary record. Shown here along the bottom axis is the origin of the planets to the present, and the height of each one of these planetary lines here in different colors represents the percentage of the surface of the planet that was formed in those periods and preserved. So, for example, on the lower right in blue, 60% of the Earth has formed in the last 600 million years, even though all the planets formed at the same time, more or less. And indeed, when we go back in time, there's woefully inadequate history represented by the Earth, and we can find that on the Moon, Mercury, and Mars. So this exploration led us up to the exploration of Venus, which was the most difficult planet to get. In the 1990s, we sent Magellan there, inventor of 1516 from the Soviet Union. And the question was, what would Venus look like? It's a large planet. Would it be like the Earth with active plate tectonics, etc., and have a very young surface, or would it in fact be like the smaller terrestrial planets and have a completely crater density, high density of craters on the surface dating from that time? This is a real test of the role of size in planetary evolution. And of course, with Magellan, next slide please, what we found out was the first 80% of the history of Venus was gone, okay, like the Earth, but unlike the Earth, it was not characterized by plate tectonics. Rather, there was a lot of lack of record in the last few hundreds of millions of years, and apparently some major resurfacing that occurred within the last within the past billion years, sometime around 600 million years ago, or perhaps a little earlier. This is just amazing. I mean, this is amazing. Next, please. So what we have from this is Venus is revealing a geological record which is consistent with a range of geologically recent catastrophic resurfacing models. Now, if Venus is such a great Earth-like planet, you know, you're standing here on the surface and you're thinking, huh, very recent catastrophic resurfacing models. Huh, wonder how that could work on the Earth, or if it could. Well, of course it could. We just don't know when and how. So when we look at this, we see 6 different models here for, in fact, explaining that change in the evolution of Venus. We do not know what's going on. In fact, we heard these kinds of questions from Michael Way earlier about what Venus's role would play, thinking about the Earth. And of course, Walter Kiefer gave an additional one last night in the poster session. So this is really an exciting time, and indeed, I tried to outline this in my poster last night. I hope some of you had a chance to see that. Next, please. So what is the legacy here that we have? Okay, it is indeed scientific results from exploration and the Earth in perspective for our own inner solar system here. We have geological maps of the planets. We know broadly the histories. We have aspects of the atmospheres, and we know the geological records. And it indeed provides really important framework for our understanding of exoplanets, as Stephen pointed out in the initial talk. Next, please. So let's think a little bit about what the two communities can do to come together. This is such a beautiful synergistic time, as this conference has so beautifully shown. It's just been great and frustrating at the same time to sit here on essentially Stephen's Zoom site and hear everything, but not be able to really participate. So let me just say a couple of things. Of course, for solar system community, untold numbers of individual examples of planets, systems of planets and stars, huge parameter space is another framework for our understanding. And of course, as we've seen in the last couple of talks, exoplanets offers real insight for us in the development of future solar system exploration strategies and missions like Venus, like Neptune, like almost everything we do needs to be thought of in this context now. For the exoplanet community, huge numbers of opportunities as well. For the solar system provides this rich and accessible record of origin, evolution, and fate of a small number of planets and satellites. The lesson learned from these, from the initial assumptions and the evolving outcomes is instructive and sobering, okay? Provides a template for exploring and understanding other planets and planetary systems. Next, please. So as we go forward here, let's talk about a few of these findings and surprises that I hope will enable us to have continued communications much in the way we talked about it in the unconferences yesterday. So let's start here with essentially planetary formation and early evolution. The original Laplacian theory of nebular condensation and planetary formation, this predicted a relatively orderly trend in temperature and pressure decay from the inner solar nebula out to the outer planets, consistent with the first order observations of the high density of Mercury, the water-rich habitable zone, and the distinctive differences between terrestrial planets and gas giants. More recent studies, of course, of the order of planet formation and its effect on planetary migration, as well as the role of giant impacts in stripping planetary crusts, have significantly modified this simple picture. The pebble accretion talk we heard yesterday, I believe, was just amazing in that context. Problems have also arisen in trying to account for the small size and volatile abundances on Mars, and also the Venus D/H ratio suggests significantly more water on Venus than on Earth. So all of these things create big new ideas to think about. Secondly, the formation and evolution of planetary crusts, shown in the lower left-hand corner there. Essentially, planetary planetary crust turned out to be distinctively un-Earth-like, with primary crust generated by accretional energy, producing magma oceans and a pelagic-glazed flotation crust on the moon, and secondary crust by partial melting of the mantle. And not fully understood is a transition from primary to secondary crust on bodies where pelagic-glazed flotation is unlikely to have happened, like the Earth, Venus, and Mercury. Thirdly, tectonic systems and heat loss mechanisms, as shown in the lower right-hand diagram there. Terrestrial planets, including Earth-like Venus, do not have multiple lithospheric plates and don't have plate tectonics, instead being characterized by single global lithospheric plates. These are one-plate planets, and they lose heat by conduction, as you can see at the top there. The role of size in planetary evolution: small planets, Mercury and Mars and the Moon, lost heat efficiently, really efficiently, due to the high surface area to volume ratio, and this stabilized their lithospheres, and these thicken with time. And so this is another whole question. So when we take a look at volcano heat pipes mechanism shown in the lower right of the lower right diagram, this is an Ionian diagram. Io is losing its heat from volcanic heat pipes, the Earth plate recycling, and then of course lithosphere today shows Mercury, Mars, and Venus in there, but Venus is oscillating somewhere in this diagram here, so this is really important to find out. The first order internal structure of the terrestrial planets is known, but the details of mantle composition and convection, scale lengths, the Rayleigh numbers, and history, and not uniformly known, or they're not uniformly known or understood. Planetary scale and crustal and magnetic fields have been detected, but the cause of their generation and the nature and timing of their evolution and or their demise is really not very well known. If we take a look at essentially petrogenetic evolution, this is another area of extreme interest. The composition, including volatile content, percent partial melting, oxygen fugacity of mantles producing secondary crusts are likely to have been quite different from the Earth, and indeed to have varied over the course of geological time. This is the scary part of it, okay? The details of terrestrial planet mantle evolution are largely unknown. Next slide, please. If we take a look here at planetary processes, for example, impact cratering has clearly played a major role in all aspects of early planetary history, including primary crust formation, the volume, styles, and flux of planetary volcanism, as Marty and others have pointed out here recently, varied significantly throughout history, related to initial volatile content, related to lithospheric heat loss mechanisms and planetary compositional layering, and tectonic style and importance varied substantially with one-plate planets, in which they were dominated by vertical processes like uplift, loading, and essentially flexure, in contrast to the lateral dynamics associated with plate tectonics on the Earth. As far as planetary atmospheres go, first-order observations have been made on current atmospheres of the Earth, Venus, and Mars, but great uncertainty exists about their formation and evolution. A key question in my mind is, how do we distinguish between primary atmospheres and secondary atmospheres? What are the major processes and rates of acquisition and loss to space, as David Brain pointed out? How did Venus acquire and retain its runaway greenhouse atmosphere? Was early Mars warm and wet or cold and icy, and how did it evolve to its current state? What role did the evolving sun have on climate and atmospheric retention? And how do stochastic processes such as impact cratering influence atmospheric formation, evolution, and loss? Okay, so let me point out the habitability, spin axis orbital parameters. These are also really incredible and critical. Shown in the right-hand upper part there is a paper we published in Nature in 2003. Variations in planetary obliquity, eccentricity, and precession have been shown to have a significant influence on climate and the migration of volatile species. Deposits we see all over the place on Mars that would give you a rather unusual view of Mars if you had viewed it in the past. The huge Tharsis rise on Mars is likely to have caused true polar wander, but the timing and magnitude is not very well known. And 10th, geological history. The early stabilized lithospheres of the small terrestrial planetary bodies have provided an invaluable record of impact, volcanic and tectonic history that may have operated on the Earth and Venus earlier in history. And this is largely the missing history of these planets. The 11th one, habitability. We've talked about this. The exploration of Mars and outer planet satellites gives us potentially new ideas here, but clearly exoplanets hold huge promise there if we can figure out the way to crack the code. And there's one last one, number 12, which I didn't put in here. which is something we should all remember, which is essentially the sun is a variable star. Solar behavior is variable. This has huge influence on planetary evolution. Next, please. Okay, so just a quick couple of words on some perspectives and caveats. Terracentrism. We know the recent Earth so well that we view everything through this lens. It took decades to appreciate the role of impacts in Earth history. As Rodney Brooks has said, the retreat from specialists has become a rout. We got the call from Copernicus a long time ago, and we should heed that. Okay, uniformitarianism, this concept has served geologists well in the last centuries, weaning us from essentially biblical deluge interpretations, as you can see on the right there, but has been kind of built in a distinctive distaste for the inevitable stochastic processes, and these are critically important. Stochastic processes, punctuated stochastic events like impact cratering, are a fundamental part of planetary evolution. We need to wean ourselves from the uniformitarianism concepts. The promise and pitfalls of paradigms. Paradigms are essential in making sense out of a complex universe, but we really need to think about Kuhnian revolutions. Read the book, it's really great. These are inevitable and necessary, so we need to keep an eye out for those data that don't fit the paradigm. The space-time continuum. Take a look down in the middle diagram there, space and time. We spend virtually all of our time in the lower left-hand corner, and the Snapchat generation has pushed us perhaps even further down into that lower left-hand corner. We really need to spend a lot of time in deep space and deep time, where the star is out there and beyond. Geologists like to think of themselves as spending their time in deep space and deep time. Astronomers put us to shame and make us think in really deep space and really deep time, and we need to talk to each other about that. And finally, don't forget option D. My friend Tom McGetchin, when we were thinking about what, say, like a Magellan like Venus mission would show, would say might be A, might be C, might be B. He would say, don't forget D, which is none of the above, which indeed is what Venus turned out to be. Next, please. So we're lurching towards conclusion here. So the Earth Solar System Comparative Planetology, we have many fundamental problems remaining, not the least of which is Venus. Next, please. On the other hand, Stephen Kane came to me a couple of years ago and said, Jim, I got a problem. I need your help. I have 50 Venuses. What do I do with them? This was so exciting to me. Absolutely amazing. And again, further fuel my real love of exoplanet exploration and what we have today, which is the next slide, which is indeed essentially the era of comparative planetary systems, an era of collaboration between astronomers and planetary geoscientists. I mean, this is really an amazing time, amazing time. Einstein is purported to have said at the beginning of the nuclear age, everything has changed but our way of thinking. And that is really true, as exemplified by the last couple of days of deliberations. As of yesterday, I checked this, we have 4,116 confirmed solar system objects, okay, exoplanets, if you will, and indeed we have 3,056 planetary systems. So we're on our way, and we have, in fact, incredible tools. Next, please. In addition to tests, we have the James Webb Telescope coming online. We heard all about this. I'm probably the only one in the room that knew, actually, James Webb, an amazing, amazing man. And I would just to say that if he were alive today, he would be sitting in the front row. Okay, he would be urging us on to collaborate and build new bridges to new solar systems and beyond. And he would be also thinking about the ways in which he could personally himself, as administrator of NASA, make it happen, okay? So let's take his challenge, next slide please, and do it, okay? Let's play marbles together, and let's really do it. I think we're well on our way here. This has been an incredible conference, and the last slide, in fact, just gives my, next slide please. This is kind of where we are right now, so let's keep it up, okay? So thank you very much, and I really appreciate you coming to the conference and really making some major contributions here.